Righto guys, today what we're going to go through is the application for this section. This section is to do with uniform circular motions. Obviously the application is going to have some sort of importance and involve uniform circular motion. So the application for this part is banking angles. So roads are generally, nice and flat, nice straight road. No need to go around corners, blah blah blah, so you don't really need any sort of help. So if you can imagine a car travelling along this nice straight stretch of road, nice flat surface, we have a couple of forces acting on this car. We have a gravitational force downwards, so mg, and we have a reactionary force, so Newton's third law, reactionary force straight upwards, yeah, the normal force straight up, and that normal force is perpendicular to the road surface, so the road can't really push sideways. Road can only apply a force outwards or perpendicular to its surface, and that's kind of important to remember. Okay, so here's your car driving along. There's only really one way that you're able to turn a corner, and that is to turn the wheel, and that will introduce some sort of frictional force, and that frictional force provides the centripetal force. So that centripetal force provides centripetal acceleration, centripetal I can't be bothered writing a whole bunch of stuff. The centripetal acceleration, and remember that you need a centripetal acceleration provided by a centripetal force to undergo uniform circular motion. So in order for this to actually happen. Alright, it's a really important concept to kind of get your head around. Lots of objects go in orbit, so protons have electrons orbiting around them. The sun has a whole bunch of planets. We have a moon, we have some satellites. Saturn has the rings full of dust and rock and whatever, and our solar system has the Oort cloud wandering around the outside or through the middle of it. So this stuff here is actually, is really important. It's also really powerful. So when we want to go a little bit faster, what we can do is take this example here and basically just tilt it. So if I get my road surface, and instead of it being nice and flat, I do that to it. So it was there and now it's here, so I've kind of changed it by angle theta. What that means for my, sorry, that's my phone, what it means for my poor little car is still applying a force downwards. It can't apply that gravitational force anywhere but straight down towards the centre of the earth. However, the road surface itself can't do anything other than apply a force perpendicular to it. So it has to apply a force that balances out gravity somehow, but it can only apply, wow that's horrible, can only apply forces that are perpendicular to the road surface. Now, this is useful to us. It's kind of a bit strange, but it's actually very useful to us because the vertical part, so the normal force in this case would be the hypotenuse, the vertical part here is actually exactly the same size as our gravitational force, and that's really important. If it wasn't, the car had sent towards the centre of the earth, and you don't really need that. But because we have this guy here going upwards, this one here diagonally, we've kind of instantly created that one, a third force. So it's a force triangle, everything balances out. And that guy there, you guessed it, is our centripetal force, which will provide some sort of centripetal acceleration, so our car will move in a circle. So, just so happens that we can have friction, in this case, just as much as we had over here, and we have the centripetal force as well. So both of these are providing some sort of centripetal acceleration, and that means we are turning the corner. What this kind of means is that we don't actually need to rely on friction anymore. We can use the centripetal force to provide all of the this guy here, the centrifugal force is created up here because the road's been banked. We can use that to supply all of the turning force for the car. The beauty of this is that now we can go faster around corners. Everyone wants to go faster, but we can also go faster safer. We are relying less on friction, so less friction means less tyre wear. That's good for you in terms of buying your first car and having to put new shoes on it all the time. We're also using less fuel because you're not slowing down towards the corner because you can go a little bit faster around it. So you're not having to brake, and you're also not having to re-accelerate coming out of the corner at the other end. Kind of means that you're maintaining a more constant speed, which means you're going to use less fuel in the end. All right. The drawback, though, is that it doesn't actually matter. Well, maybe not a drawback. It's probably almost a good thing. It doesn't matter what sort of vehicle it is. So, little kid in a Razor scooter all the way through to a fully loaded B-double. Mass is irrelevant, or mass is not important. Okay, so I'm going to explode this thing up with that guy. So here is centrifugal force, mg, my normal force, my angle theta. A little bit of trig now, guys. Tan theta is opposite over adjacent, fc over mg. So remember, fc is, we can use ma, so mac. A is v squared on r, so all I'm doing is m equals v squared on r. Now I'm going to sub that into here. So my fc becomes mv squared on r over mg. That cancels out with that, equals v squared on rg. So as you can see, mass is not important because there's no mass in my equation down here. So this guy tells us how fast you can go around the corner of a specific radius without relying on friction whatsoever. So we don't need that if this v squared on rg is equal to our tan theta. Our theta angles are kind of low single digits, 3-4 degrees, all the way up to somewhere around 13 degrees. Anything over that's just a little bit too steep, kind of becomes a little bit of a hazard itself. So these sorts of things are great, especially if you're a little old lady and you driving an old car and you don't have much strength, and you also don't have power steering. Means that you don't actually need to rely on friction. If you don't need to rely on friction, you also don't need to turn your steering wheel. So you can actually cruise around a corner relying just on the centrifugal acceleration, and it will make you go around the corner. This here is the application for the uniform circular motion section of the course. As you can see, it's actually really, really handy. Velodromes use this, NASCAR tracks use this, IndyCar tracks use this. Next time you drive around the hummocks, you'll probably understand that you don't need to yank as hard to the left or the right as you're going around the corners, and it's all because of this thing here, so this relationship. Tan theta equals v squared on rg. All the questions you get are going to relate to this guy for this section of the course. So you might be asked to find the speed, you might be asked to find the radius, you might be asked to find the banking angle. G is gravity. So that's obviously not going to be the thing you have to find. So all you might have to do is rearrange that based on the numbers that you're given in that section, in those sorts of questions. Okay,